Hi everyone, we are going to be going through chapter 5, and that is analytic trigonometry, which includes using fundamental identities, verifying trig identities, solving trig equations, sum and difference formulas, and multiple angle and product to sum formulas. So I'm going to be out for this week, and I might use this video for future classes of mine. So let's get started. First, our first page says identity crisis. And it says, we know that sine, cosine, and tangent all represent ratios of sides in a right triangle, but are they related in any other way? And what do cosecant, secant, and cotangent have to do with it? Okay, so we're looking at this diagram. It says a circle of radius 1 is drawn to in the first quadrant. Segment DB is tangent to the circle at point A. So that means that DB, the blue line, touches the circle once at point A. What is the length of AC? And then explain why segments AF represent sine and which other segments represent sine. Okay, so the length of AC, I can draw over right here. It's this black line. But we were told that we have a circle with radius 1, and AC is the radius of that circle. So I'm going to say AC equals 1. And then it says, explain why AF represents sine of theta. Well, in right triangle trig, right, if we're looking at theta, or angle theta, sine of that angle would be opposite over hypotenuse. Okay, which this hypotenuse happens to be 1. We just said AC equals 1. So in this case, sine of theta equals this red segment, which is AF, divided by 1. So sine of theta, single theta, equals AF divided by 1. Okay, and then AF divided by 1, doesn't that just equal AF? And so segment AF equals sine of theta. And then it asks which other segment represents sine of theta. Well, that would be this segment over here, EC, because they are equivalent or congruent segments. Okay, then let's see, sine of theta equals AF. We can also say sine of theta equals EC. Then explain why CF represents cosine of theta. Okay, let me erase red. And we're going to be working with green. Okay, so segment CF down here, if we're working with this angle theta again, theta, cosine of theta is going to be adjacent divided by hypotenuse. Okay, so I'm going to write cosine of theta is equal to adjacent over hypotenuse. Our adjacent segment is CF, and our hypotenuse is 1. So doesn't that mean that cosine of theta equals CF? Because CF divided by 1 is just CF. And then which other segment represents cosine of theta? That would be AE. And I'm going to actually just leave the divide by 1 over here so that we're answering the question, explain why. Okay, then it says, what is sine squared plus cosine squared? How do you know? Okay, well, sine squared would be AF squared. So this red side squared plus CF squared. Well, wouldn't that equal the hypotenuse squared? Which in this case is 1 squared, and that's 1. So I'm going to write this sine squared theta, or sine theta squared and sine squared theta are the same thing. So sine squared theta plus cosine squared theta is going to equal 1 squared, because that's like using the Pythagorean theorem, right? A squared plus b squared is going to equal 1 squared. And we know that 1 squared is 1. How do I know? Pythagorean theorem. Okay, then it says, what is the relationship between angle theta and alpha? Well, I'm looking at this picture and it seems like together they create a 90-degree angle. So I'm going to say theta plus alpha equals 90 degrees. And then it says label all the other angles in the diagram with a theta, alpha, or 90. Remember from geometry that a tangent line is always perpendicular to the radius at the point of tangency. Okay. So let me erase some of this. All right, so from alternate interior angles, I can say this angle is also theta, and then this angle is alpha, and those add to 90. And then here's another 90, here's another 90. And then if we know that right here is also 90, like angle DAC, that means that we need another alpha here, because alpha plus theta equals 90, and we have 90 degrees at that angle DAC, that has to be alpha. And same thing over here, if we have angle CAB, that equals 90, we have part of it is alpha, the other part needs to be theta. And then there's two other angles. Let's look at this smaller triangle DEA. We know this is a 90 degrees right here, and so we need another 90 to be part of this triangle to make it 180. So we have 90, and then we have alpha. The other part would need to be theta, because theta plus alpha equals 90, and then 90, 180. Same thing for this larger triangle, FAB. We have 90 right here, then theta, so this other angle needs to be alpha. And then it says, what do you notice about the angles in ACF and BCA? Well, in ACF, we have alpha, theta, and 90. And in BCA, we also have alpha, theta, and 90. So since those triangles have the same angles, although they're different sizes. Here's the first one, ACF, I'm outlining in black. And then BCA, I'm outlining again in red. Oops. BCA is this larger one. Then these are similar triangles because they have the same angles. Okay, then it says, let's see what we can find out about the ratios in this triangle. Fill in the missing proportions. Okay, so AF over FC. So AF divided by FC is equal to something divided by AC, and AC is our shorter side. So if I'm looking at the black triangle versus the red triangle, okay, and we just said that they are similar. So AF is the longer side, and FC is the shorter side. Then in the red triangle, that's going to be the same as AB, which is the longer side, divided by AC, which is the shorter side. Okay, and then rewriting this with what we already know, we get the proportion below. Which trig ratio should we use to label AB? Well, sine over cosine we know is tangent theta. So doesn't that make sense? Since we said up at the beginning that that segment is tangent to the circle at point A. Okay, we are going to move on to the next page. I think your guys' notes don't include this page, so we're going to skip here. And we are going to first review some important trig functions. We know that sine of theta divided by cosine of theta is tangent theta. And then 1 divided by sine of theta is cosecant. And 1 over cosine theta is equal to secant. And I didn't say it before, but you should be following along with me and writing this in your note packets at the same time that you're listening. Okay, then Pythagorean identities are what we're learning right now. And you actually already found one. Okay. The first one is sine squared theta plus cosine squared theta equals 1. And we came up with that equation using our Pythagorean theorem. And so that's why it's called a Pythagorean identity. Okay, now there are 2 other Pythagorean identities, and they derive from this first one. So I'm going to show you how to derive it. To get the second Pythagorean identity, you can divide everything by sine squared. Now I'm going to end up erasing this blue writing, so don't feel like you have to copy it right now. I'm just showing you how to get to the next identity. So sine squared divided by sine squared is 1. Cosine divided by sine squared is cotangent squared. And then 1 divided by sine squared is cosecant squared. Okay, and then that's how we got the second Pythagorean identity. To get the third Pythagorean identity, I am going to divide everything by cosine squared. And when I do this to both sides of the equation, I'm not changing the value of the equation. I'm just making it look different, okay? So sine squared divided by cosine squared is tangent squared. Cosine squared divided by cosine squared is 1. And then 1 divided by cosine squared is secant squared, okay? So I would recommend memorizing this first equation, and then you can always get the second and third Pythagorean identities by dividing by sine squared or cosine squared. Let's practice. Okay, so this first question is kind of right triangle trig. So it says if secant is 7 over 2, find the other trig functions. So I'm going to draw a right triangle, theta, and then secant is 1 over cosine. So that means that cosine is actually just the reciprocal of this, which would be 2 over 7. So I'm going to start with that. Cosine is adjacent over hypotenuse, 2 over 7. And then I need to find this other side length. So let's use Pythagorean theorem. 2 squared plus x squared equals 7 squared. 4 plus x squared equals 49. X squared equals 49 minus 4, which is 45. And then x equals root 45. And we're going with the positive value since this is a length. You can't have a negative length. This is going to be positive root 45. And then now it's easy to get those other trig values. So tangent of theta would be root 45 over 2. You know what? Let's simplify root 45. I forgot to do that earlier. So 45, you can write that as 5 times 9. And then we know that the root of square root of 9 is 3. This is going to be 3 root 5. Okay. So let's change this. Okay. Let's do sine theta is 3 root 5 over 7. Cosecant theta is the reciprocal of that. And if you want to make sure the radical is in the numerator, you can say 7 root 5 over 3 times 5, which is 15. And cotangent is going to be the reciprocal of tangent, which is 2 over 3 root 5. And if you want to simplify that and put the radical in the numerator, you can have 2 root 5 over 15. All right, number 2, simplify each expression to one number or one trig expression. So this is when we're going to start using our trig identities up above, our Pythagorean identities, to simplify some expressions. This first one, actually you don't need our Pythagorean identities. You just need this stuff up here and what you need to know what tangent is and what cotangent is. And we're going to rewrite these trig expressions in order to simplify them. So tangent, I can rewrite it as sine theta over cosine theta. And then cotangent, I can rewrite it as cosine theta over sine theta. And then it just so happens that sine divided by sine is 1, and cosine divided by cosine is 1. So, and then 1 times 1 is 1. So this whole thing equals 1. And I want you to keep track of the different strategies we use. Here's our first one for simplifying trig expressions. We're going to rewrite everything in terms of sine and cosine. Okay. Next, this expression has 1 minus sine squared in it, which should seem familiar to us because we have a 1 and a sine squared up here, okay? But we don't have, I'm looking for 1 minus sine squared. I don't necessarily have that yet. But is there anything, could we change this equation around to have a 1 minus sine squared? Well, yes, we could subtract sine squared from both sides. And then we'd get a new equation, or we would just isolate cosine squared. Cosine squared equals 1 minus sine squared theta. So in place of 1 minus sine squared, I could write cosine squared theta. And I'm going to erase this so that we can come back to it if we need to. But we just said we can rewrite this as cosine squared theta using our Pythagorean identity. Actually, I can write it over here. Sine squared plus cosine squared equals 1, and then I subtracted sine squared from both sides. Okay, and then I'm going to bring this down. And then let's rewrite secant squared. Secant squared theta is just 1 over cosine squared theta times cosine squared theta. Whoa, that ends up equaling 1 as well. Cosine divided by cosine squared, or cosine squared divided by cosine squared is 1. Okay, here is another strategy we just used, is find Pythagorean identities, or let's say rewrite using Pythagorean identities. And sometimes it's hidden, right? This didn't exactly look like a Pythagorean identity. We had to change our Pythagorean identity around a little bit to get exactly what we wanted, okay? But we did use a Pythagorean identity. All right, next, this one, the Pythagorean identity is right there. It's not really hidden at all. Cosine squared plus sine squared is, and hopefully in your head you just said 1. And then secant x is below. 1 over secant x, or the reciprocal of secant x, is cosine. And then that is the simplified answer. So our first two equaled 1. Sometimes they equal just a single trig function. Okay, and that one we used a Pythagorean identity again, so I'm not going to write another strategy. We already had that one. Okay, here we go. Secant squared minus tangent squared. How can we rewrite this or simplify? Well, I feel like it is similar to this third Pythagorean identity, tangent squared plus 1 equals secant squared. So I'm going to write it down here. Tangent squared plus 1 equals secant squared. Okay, but I'm looking for secant squared minus tangent squared. Well, couldn't I just subtract tangent squared from both sides? And then I do have secant squared minus tangent squared, and that's going to equal 1. Okay, so I manipulated this Pythagorean identity to isolate for 1, and I got secant squared minus tangent squared equals 1. Okay, number 6 is a challenge. I want you to pause the video and try on your own. And then you can unpause and watch me do it. Okay, here we go. So cosecant x, I can rewrite as 1 over sine x. Cosine, I can't really change, but I can change cotangent to be cosine over sine. Okay, then I'll write this as cosine over 1, and then I can simplify this to be cosine squared on the top divided by sine x. And then the first term I'm going to leave as is, 1 over sine x. But now it looks like I have two fractions, but they have the same denominator. So I can add and subtract fractions of the same denominator. So I'm going to put them together as 1 minus cosine squared over sine x. Okay, and now this numerator is looking very similar to a trig identity. Looks very similar to this first one. So I'm going to write the first Pythagorean theorem, or Pythagorean identity, off to the side. And I'm going to manipulate it so that I can have 1 minus cosine squared. So subtract cosine squared from both sides. And I get sine squared x equals 1 minus cosine squared x, which is what I wanted. So instead of writing 1 minus cosine squared x, I can just write sine squared. So sine squared is now in the numerator, sine x is in the denominator, and sine squared x divided by sine x is just sine x. Okay? So nice job on that. We actually added one more strategy there. We added or subtracted fractions with the same denominator, okay? So you can say add or subtract fractions is another strategy. But for that strategy, you do need the same denominator. So sometimes you're going to have to create a common denominator. All right, that is the end of lesson 5.1a. Nice work. All right, on to the next section. Our warm-up is what are the 3 Pythagorean identities? So let's write those down. Try and do that. Pause the video and try and do it on your own, and then check back. We have sine squared theta plus cosine squared theta equals 1. And then if we divide everything by sine squared, we get 1 plus cotangent squared theta equals cosecant squared theta. And then if we divide our original equation by everything cosine squared, we get tangent squared theta plus 1 equals secant squared theta. All right, then it says on the left is a right triangle. Draw in the right angle symbol at the right angle, okay? And then one angle is labeled alpha. In the diagram, write in the value of the other angle in terms of alpha. Well, if this is 90 And then we have alpha. The other angle must be 90 minus alpha. Oops. So that our whole triangle adds up to 180 degrees. And then it says, now we're going to come up with some relationships, and you're going to be given the basic trig functions of alpha. How do they relate to the trig functions of the other angle? Okay, so I'm going to go through this. If sine of alpha, that would be opposite over hypotenuse. Okay, but how does that relate to the 90 minus alpha angle over here? Well, this side is actually the adjacent by hypotenuse. So sine of alpha would be the same as cosine of 90 minus alpha. And then let's do another one. Tangent of alpha is opposite divided by hypotenuse. But if we're looking from 90 minus alpha, that's going to be adjacent divided by opposite, which is cotangent of 90 minus alpha. And then you'll start to see sine and cosine go together, tangent and cotangent go together. So secant, if you guessed, will go with cosecant of 90 minus alpha. Similarly, cosine of alpha will be sine of 90 minus alpha. Cotangent of alpha will be equal to tangent of 90 minus alpha. And cosecant will be equal to secant of 90 minus alpha. And it says down below, because of these beautiful relationships, these trig functions are called cofunctions. Cosine and sine, cotangent and tangent, cosecant and secant. Okay, so if we wanted to rewrite sine of 20 in terms of cosine, we could say cosine of 90 minus 20 or cosine of 70. And then if we wanted to write cosecant of pi over 11 as secant, we could do secant of, well, it'd have to be pi over 2, which is 90, minus pi over 11. And to do that, we would need a common denominator. So let's do 11 pi over 22. I'm multiplying this first fraction by 11 over 11. And multiplying the other fraction by 2 over 2. And then we get 2 pi over 22. And when we subtract them, we get 9 pi over 22. So cosecant of pi over 11 is the same as secant of 9 pi over 22. All right, let's go to the next page. Here you're going to use Desmos, and you can work with a partner or individually. And you're going to decide which equations are equivalent. So I want you to, in one, like Desmos.com, the graphing calculator, you're going to plug in sine of negative x, sine of x, and negative sine of x, and graph them all on the same plane, and decide which of the two are the same. Okay, and circle those. And you're going to do that for each of these rows, and there will be always two equations that match up. So go ahead and do that, pause this video, and then you can come back and check your work. All right, so coming back, this is what you should have had. If you notice, the ones that are different are cosine, because because when you plug in cosine of negative x, you end up getting the same cosine of x. And secant of negative x equals secant of x. Other functions are different, and we can relate this back to semester 1. These are even functions, okay? So when we plug in negative x into our function, like f of negative x, and it equals the original function f of x, that is an even function, and it is symmetric across the y-axis. These other equations are odd functions. So sine, tangent, cosecant, cotangent are odd. Cosine and secant are even functions. So that's one of the patterns you might have noticed. And I'm just going to write that cosine and secant are the only even functions. Okay, next it says find the exact value of the expression without a calculator. Okay, so we're going to use some strategies to rewrite. And actually, we can add to our strategies. I've been using a yellow marker and a star. Another strategy we can use is to rewrite using cofunctions. So we can rewrite expressions using cofunctions. Okay, and at some point I'm going to put a list together with all the strategies of how to simplify expressions. But just as we're going along, we're noting them here. I'm going to use that strategy. And cosine of 10 and sine of 80 can be written as cosine of 90 minus 80, which actually ends up being 10. So, actually, I'll write this out. So then we get cosine of 10 degrees divided by cosine of 10 degrees. Or you could have written out cosine of 10 equals sine of 90 minus 10, which is 80. And you get sine of 80 divided by sine of 80. Okay, then over here, same strategy we can use. I can rewrite this cosine of 20 using cofunctions. So I could do, instead of minus cosine squared of 20, I could do sine squared of 90 minus 20, which is 70. And then I have a very interesting expression here. This reminds me of sine squared theta plus cosine squared theta equals 1. Okay, it doesn't look quite like that, but is there a way, like I could maybe get 1 minus sine squared of theta? Well, yeah, if I subtracted sine squared theta from both sides, I get cosine squared theta equals 1 minus sine squared theta. Okay, so 1 minus sine squared theta, I can just replace with cosine squared theta. So I'm going to take this 1 minus sine squared 70 and then replace it with cosine squared 70. And then copy this down, cosine squared 70. But now it's just like I have cosine squared 70 minus itself, which equals 0. All right. Next, this is another Desmos activity that you're going to use. And I'm asking you which of the equations are identical. So graph them on the same page to find out. And you're going to, again, compare rows. So is this equation equivalent to tangent of x? Graph them out and see if they line up. And the same for B and C. And then come back and find the answer. Okay, so you should have gotten the first two are not the same. The second two are, okay, so this 4, very complicated on the left. 4 times 3 squared times cosecant minus 1 times secant x plus tangent x divided by cosecant secant x can be reduced or simplified or is the same as 2 times 3 cosine squared, okay? And these other two were not the same. The reason I had you do this is because I want to show you, kind of lead into what you will be working on the next activity. But we're going to start taking two equations or two expressions and proving that they're equal. So when you start verifying trig identities, you're going to have to prove that something like this does equal that. Okay, so let's go to the next page. And we're just going to summarize what we've learned during this activity. Okay, so first we learned about cofunctions. And we're just going to write them all out here. Sine of, you can do 90 minus alpha. You can also do pi over 2 minus alpha, or theta, sorry. Equals cosine of theta. And I'm just going to write all of these out, and you guys can copy them. Okay, so maybe pause it here and go ahead and write down, copy those cofunctions, and then we're going to write out the even and odd identities. And again, I'll write them out and you can pause it and copy. All right, so go ahead and copy these identities that we talked about earlier. And remember that cosine and secant are the only even identities, and the other ones are odd. Okay, and then we can do some check understanding. So it says simplify the following, and we're going to use some of our strategies that we've learned along the way. First, tangent and cotangent. The strategy I think I'm going to use is just writing everything in terms of sine and cosine. We might have done this problem already. So sine of theta divided by cosine of theta times cosine over sine, and that ends up equaling 1. Okay, number 2, I'm also going to put in terms of sine and cosine. So the numerator would be cosine x over sine x. And then we're dividing by 1 over sine x. Okay, and then how do we divide two fractions? Well, we can multiply by the reciprocal. So I'm going to take cosine x over sine x and multiply by the reciprocal of 1 over sine x, which is sine x over 1. And then sine x divided by sine x is 1, so we're left with cosine x. Next, secant times sine x. Here I'm also going to rewrite in terms of sine and cosine. So this first one, secant, can be written as 1 over cosine times sine over 1. And I know that sine x divided by cosine x we could write as tangent x, and that is our fully simplified answer. Okay, next. sine squared divided by 1 minus cosine squared. This does remind me a lot of my first Pythagorean identity, so I'm just going to write it up here to have it handy. And the denominator, I think I could make a 1 minus cosine squared. I can just subtract cosine squared from both sides. And we end up getting sine squared equals 1 minus cosine squared x. Okay, so that means I can replace this denominator with a sine squared x. So it ends up being the numerator is sine squared x, and the denominator is sine squared x. So we get 1 again. And then over here, this also reminds me of a Pythagorean identity. It reminds me of this one where we have, actually, let's do a different color. Tangent squared x plus 1 equals secant squared x. Okay, so that means I can take this tangent squared plus 1 and rewrite it as secant squared x times cosine x. And then I can rewrite secant squared in terms of cosine, which is 1 over cosine squared. So we end up getting cosine x over cosine squared x. One of those cancels. Cosine divided by cosine is 1. So we're left with 1 over cosine x, which ends up being secant x. All right. And that is it for 5.1b. All right, we're going to get started now with 5.2. And we're just going to do a lot of practice problems, add some things to our strategies list, and work through them. So here we go. This first problem says to factor out a monomial, which means factor out a term that is common in or an expression or a trig function that's common in both terms. So I'm looking, the first term has a sine x and a cosine squared x, and the second term has a sine x. So I'm going to factor out sine x. And what's left is going to be cosine squared x minus 1. And that reminds me of a Pythagorean identity. Okay, cosine squared x minus 1, I can do some maneuvering to make our identity look like that. So I can subtract sine squared from each side. And then I can subtract 1 from each side. So then I get cosine squared x minus 1 equals negative sine squared x. Okay, so now I can take this cosine squared x minus 1 and replace it with negative sine squared x. Bring down the sine x that was already there. And now we just have to multiply them together to get negative sine cubed x. Okay, so here's a new strategy we use is to factor out a monomial. So I'm going to put a yellow star there. All right, next it says factor. And looking at this, you might not know what to do right off the bat. But here's like, this is another strategy is to factor our trig functions. But sometimes something that helps me is creating an easier problem first, and then like an algebra problem, and then bringing back our trig function. So at first, I'm going to take out secant squared. I'm going to let secant x equal a for right now, okay? So instead of a secant squared, I'm going to write this as a squared minus 1. Or you could also write it as x if it doesn't get too confusing. Okay, I could write this as x, instead of secant squared, I'm just going to write it as x squared minus 1. And this is a lot of easier problem. This is like algebra 1, right? Difference of squares. And that's essentially what we had before. We had a difference of squares. This was a secant squared minus 1, which is also a perfect square. But x squared minus 1, we know how to factor that. It's x plus 1 times x minus 1. And that's just the pattern of factoring out a difference of squares. But now I have to go take x and replace back secant x with it. So I'm going to put the trig function back in. Okay. And that was a kind of a tool that I like to use, is to create an algebra 1 factoring problem first and then bring back the trig function into it. But you are more than welcome to go from the first step to the second step. You do not have to do this in between. Okay. Let's do the next one. This is a little trickier, but same type of thing, right? We have 4 tangent squared x plus tangent x minus 3, and we're supposed to factor it. So I'm going to let tangent x equal x for a second, and then it's going to be 4x squared plus x minus 3. And that is now an algebra 1 problem. And I can easily factor that. For x squared, I can put a 4x and an x. And then 3, you can do minus 3 plus 1. And then you can kind of check to multiply it out to make sure you got the correct answer. So 4x squared plus 4x minus 3x minus 3. Well, 4x minus 3, x is 1x. So we did factor it correctly. Okay. So this is just like my checking my work. All right. So now we're going to replace all my x values with tangent x. So 4 tangent x minus 3 times tangent x plus 1. And again, you can go from here, you can go from here to here, and you don't have to do any of the substituting if you don't want to. All right, number 3. Factor, again, cosecant squared minus cotangent x minus 3. All right, so this one is a little different because the other factoring ones, or at least B, I had like tangent squared and tangent. Okay, it was the same trig function, but now these two are different trig functions, so I don't really know how to factor different terms that are not, having the same trig function. So I'm going to see if there's any way to make them into the same trig function. All right, so do we have a Pythagorean identity, possibly, that includes cosecant and cotangent? Well, we do, okay? It is 1 plus cotangent squared equals cosecant squared. So instead of cosecant squared, I can just write 1 plus cotangent squared x. And now everything is in the same, has the same trig function. So let me clean this up a little bit. 1 minus 3 is negative 2. So to rewrite this, I'm going to write cotangent squared x minus cotangent x minus 2. And then we can factor, okay? So I'm going to do an example where I'm not using the algebra 1 example, okay? So this one I can just write, okay, cotangent times cotangent equals cotangent squared. And then to multiply to -2 and to add to -1, I'm going to get a -2 plus 1, okay? But if you wanted to, you could rewrite this as x squared minus x minus 2, then factor that, and then bring back the trig function, okay? And we're done because it just told us to factor. It didn't tell us to solve anything. All right, this next problem says simplify sine t plus cotangent t times cosine t. Okay, I'm first going to get everything into sine and cosine, and hopefully that can help us out. So cotangent can be written as cosine over sine, and then we're multiplying by cosine. And then I can write this as one fraction, and it's going to be cosine squared t over sine t. Okay, and now I'm kind of adding fractions because it's going to be over 1. So let's get a common denominator. I'm going to multiply this by sine of t over sine of t. And then I can rewrite this as sine squared t over sine of t plus cosine squared t over sine of t. And what do these equal if we add these fractions together? It equals 1. So we have 1 over sine of t. And the reciprocal of sine is cosecant. So that is our answer right there. Okay, our next problem says rewrite 1 over 1 plus sine t so that it is not in fractional form. And we're going to add a new strategy to our bank today, and that is when we're trying to get something out of a fractional form, we can use conjugates. And if you remember from, I think it was first semester, a conjugate of a plus bi would be a minus bi. So in this case, 1 plus sine x on the bottom, the conjugate of that would be 1 minus sine x. So I'm going to take 1 plus sine x, and I'm going to multiply it. So when I'm multiplying by the top and bottom, I'm not, or the numerator and denominator, I'm not changing the value of the fraction. But I'm going to multiply by its conjugate, okay? And you're going to see how we will get this out of a fraction. So in the numerator, we have 1 minus sine x. In the denominator, let's multiply this out. 1 times 1, 1. 1 times negative sine. Sine times 1, sine. And sine times negative sine is negative sine squared x. Okay, let's clean this up. In the numerator, we still have 1 minus sine x. In the denominator, sine x minus sine x is 0, and we're left with 1 minus sine squared x. Wait, this does remind me of a Pythagorean identity. Sine squared x plus cosine squared x equals 1. I want to get 1 minus something that looks like 1 minus sine squared. So I'm going to subtract sine squared from both sides. And we get cosine squared equals 1 minus sine squared theta, or x. So instead of writing 1 minus sine squared x, I can rewrite it as cosine squared x. I'm going to do that down here. The numerator is still the same, but the denominator is cosine squared x. Okay. Now we are going to actually add another strategy, and we've used like adding and subtracting fractions. We can also break apart fractions. And what I mean by that is, I'll do like a simpler example over here. Let's say you have 5 plus 3 over 9, okay? We could also write that as 5 over 9 plus 3 over 9, correct? So that is basically what we're going to do, okay? Instead of 1 minus sine x over cosine squared x, I'm going to rewrite that as 1 over cosine squared x minus sine x over cosine squared x. So I'm breaking apart the fraction. Okay, and then the first term, the reciprocal of cosine squared is secant squared. And then we kind of have I'm going to write this as sine x over cosine x times cosine x. And we really have a tangent right here, and then times 1 over cosine. So I'm going to rewrite this as secant squared x minus tangent times 1 over cosine is secant. And I could maybe, if I wanted to simplify this further, maybe divide out secant x from both terms, but all we wanted to do was rewrite so that it's not in fractional form, and we got that. Okay, so that's going to be the end of that problem. Nice work. All right, next, this problem will show up, on a quiz or a test, and it looks scary at first, but it is not too bad. So let's do it together. Okay. So first it says use x equals 2 tangent theta. Theta is in the first quadrant. It's telling us to write square root of 4 plus x squared as a trigonometric function of theta. Okay, so all it's telling us is like when you see an x, plug in a 2 tangent theta instead. Okay, so I'm going to write the expression 4 plus x squared, and I see an x, and I'm going to write in a 2 tangent theta in its place, but the x was squared, so I'm going to take this and square it. Okay, now let's simplify. 2 squared is 4, and tangent squared is tangent squared. Okay, and then I have something in common between these two terms. I have a 4, so I can actually divide out a 4. And 1 plus tangent squared does look like a Pythagorean identity. So I'm going to write that one out. Tangent squared theta plus 1 equals secant squared theta. So instead of writing 1 plus tangent squared, I can just write it as secant squared. So I'm going to write 4 times secant squared. And now both of these are perfect squares. So I can take the square root of 4, that equals 2. And the square root of secant squared is just secant. okay? So I think the hardest part is maybe just the beginning, just plug in 2 tangent theta for x, make sure to square it if x is squared, and you can simplify from there. All right, we are now going to summarize and kind of prepare ourselves to verify trig identities. So when you are working and verifying trig identities, you always want to work with one side of the equation at a time. And you're going to want to work with the most complicated side. Okay, and then we'll kind of talk about why that is. But the next part, we're just going to list the different strategies we've been coming up with. I'll actually write it in yellow. So when we're verifying trig identities, we're going to look for opportunities. And these might be out of order, but we're going to look for opportunities to factor, add or subtract fractions, you can square a binomial, which we haven't done yet. I'll show you how to do that. You can create a common denominator. You can write in terms of sine and cosine. You can rewrite using Pythagorean identities. You can rewrite using cofunctions. You can break apart fractions. You can rewrite using even and odd identities. And you can use conjugates as well. Okay. The most important step or strategy, though, is to always try something. Okay, up until this point, we've been keeping track and adding different strategies to use. Going forward, you will have to use which of these strategies to use. You have to decide, which of these strategies to use. And then we're going to add some equivalent forms of the Pythagorean identities, which we won't use that much in this class. Okay, just to remind ourselves, I'm going to write the original Pythagorean identities out. And again, you have to memorize these. I usually just memorize the first one. And then to get our equivalent forms, I'm going to isolate sine here. So if I were to isolate sine, I'd subtract cosine squared from both sides, and I get sine squared equals 1 minus cosine squared. But if I wanted sine by itself, I could take the square root of both sides and get plus or minus square root of 1 minus cosine squared theta. And so that is an equivalent form. Another one you could do is, you could isolate any of these. You could isolate cosine, tangent, secant, cotangent, cosecant. Let's isolate tangent. I would get, let's see, tangent squared. I'm going to subtract 1 from each side. And then I could take the square root of both and get plus or minus square root of secant squared theta minus 1. Okay, so here's another equivalent form. All right, let's verify some identities. Okay, and this is where we said work with one side of the equation at a time, work with the most complicated side. So which side is the most complicated? Hopefully you said left. I would agree. Okay. The reason why we can only work with one side at a time is because we are verifying that they are equal. So it's kind of like we're verifying that this equal sign should be there, and you should kind of have like a question mark above the equal sign. Like, are they equal? Well, I don't know. We're going to have to verify it, okay? So if you use, like, let's say you multiplied by secant x on both, or secant squared x on both sides, okay? That would be the multiplication property of equality. And you're using, like, doing the same thing to both sides is using the fact that they are equal. So if we're trying to verify that they're equal, you can't really use the fact that they're equal, okay? So we're just going to take one side and make it look like the other. All right, so here we go. Our first problem. Secant squared x minus 1 divided by secant squared x. Well, secant squared x minus 1 looks a lot like this Pythagorean identity that we wrote out already, okay? If I subtracted 1 from each side, secant squared x minus 1 would be equal to tangent squared x. Okay, then I used Pythagorean identity. Now I'm going to try and put everything in terms of sine and cosine. So let's make the numerator would be sine squared over cosine squared. And the denominator would be 1 over cosine squared. So let me actually write this out a little bit nicer. And when we're dividing fractions, we can multiply by the numerator. Sorry, multiply by the reciprocal. So sine squared over cosine squared times the reciprocal of 1 over cosine squared, or the reciprocal of secant squared, would be just cosine squared. And then cosine squared divided by cosine squared is 1, and we're left with sine squared. And that's what we wanted to prove. Like we wanted to prove that the left side did equal the right side, and we just did. Okay, so we proved what we set out to prove. And so a lot of times when you're done with a proof, you write this little box with a slash. It represents QED, which in Latin is quod erat demonstrandum. which just means we demonstrated what we wanted to demonstrate, or we proved what we set out to prove. Okay, some people say QED means quit, enough, done, but that's just that's more just a joke, okay? It really stands for this Latin phrase, but I just am in the habit of drawing this box with a slash through it. Okay. Next, we're gonna prove that these two are equal. We're gonna verify this identity. Which side is the most complicated side? Which side should we start with? Hopefully you said the right, okay? And this looks very similar to the problem we did on the other page where we had to use a conjugate. So if you ever have like 1 minus a trig function or 1 plus a trig function in the denominator, you're usually going to want to use a conjugate. So in this case, I'm going to use a conjugate for both. Okay, so the first fraction, I'm going to multiply by 1 plus sine x over 1 plus sine x. And then the second fraction, I'm going to multiply by 1 minus sine x. 1 minus sine x. And then simplifying. And we're actually going to get a common denominator, which is nice. The numerator here is 1 plus sine x. And then multiply this out. 1 times 1 is 1. 1 times sine x. 1 times negative sine x. That will be 0. And then negative sine x times sine x is minus sine squared x. Okay, and then over here we're going to get the numerator 1 minus sine x, and we have a common denominator, 1 minus sine squared x. Okay, now we can add these fractions together. And again, we used a conjugate here for this strategy. Let's add, well, the denominators are the same, so common denominator. The numerator 1 plus 1 is 2. Sine x plus negative sine x is 0. So I'm just left with 2. The denominator looks like a Pythagorean identity, if I'm not mistaken. Okay, 1 minus sine squared. I could subtract sine squared from both sides over here. And that would be equal to cosine squared. So I'm going to rewrite the denominator as cosine squared x. And then that's just 2 times 1 over cosine squared x, which the reciprocal of cosine squared x is secant. So our answer is 2 secant squared x. Is that what we wanted to prove? Yes, it is. Okay, so we proved what we set out to prove. Nice. Okay, try this next one on your own, maybe the next two. Pause this video and then come back. All right, let's do this. The left side is most complicated here. And what I'm going to do is, actually, both of these are looking to me like Pythagorean identities. I know that tangent squared plus 1 equals secant squared. That is an identity. And then cosine squared minus 1 would mean that I had subtracted 1 from both sides and subtracted a sine squared from both sides. So this actually equals negative sine squared. And I used Pythagorean identities here. And now I'm going to rewrite in terms of sine and cosine. Secant squared can be rewritten as 1 over cosine squared. Oh, actually, this needs to be x, sorry. And we can rewrite this as negative sine squared over cosine squared, which simplifies to negative tangent squared, which is what we wanted. There we go, QED. Next, so which one is more complicated, the left or the right? It's actually going to be the left. A plus is more complicated than multiplying. Multiplying is like much more simplified than adding. So let's work with the left side. I'm going to put everything in terms of sine and cosine. And again, as you work to do more of these problems, you're going to get more comfortable with the strategies and when to use them. When you're following along with me, it'll probably be making sense to you, and yeah, I got it. But as soon as you start to try your own, it might be a little bit difficult. And I would just say, like, this unit just takes a lot of practice, and you know, for each problem, you have a lot of different strategies, and you're going to have to figure out different combinations. So don't give up, keep practicing, and it will get easier. Okay, so here I put everything in sine and cosine, and now I have two fractions. I want to add those fractions, and I think I'm going to create a common denominator in order to do that. Oops, over here it would be cosine. But while I'm creating this common denominator, I'm also seeing that I'm going to now have a sine squared plus a cosine squared, which is always a good thing, okay? So the numerator over here is sine squared. Our denominator is going to be the same for both, plus cosine squared over the same denominator, which means I can add these together. Wait, what is sine squared plus cosine squared? Hopefully you said that that's 1 in the numerator. And then we're just taking the reciprocal of sine and cosine, which ends up being cosecant and secant, which is what we wanted to prove. Okay, nice work. All right, that is all for 5.2. Next section is 5.3. All right, we are going to move on to section 5.3, and this is all about solving trig equations. And this lesson, we're just going to go through the different strategies and try and do a problem for each strategy so that when you get to do problems on your own, you can pull from these different strategies. So first strategy to solving trig equations is to collect like terms. And the difference between solving trig equations and what we've been doing is now there's an equal sign and we're solving for x. Before we were just simplifying equations or verifying, but now we are solving for x, the variable. All right, so first we're going to solve for x here. And the hint or the strategy we're going to use is to collect like terms. So I'm going to add cosine to both sides. Let's see. Okay. And then on the left, I have 2 cosine x plus root 3 and then 0 on the right. And then to get rid of, or to start isolating x, I'm going to subtract root 3 from both sides. I get 2 cosine x equals negative root 3. Then I can divide by 2, and cosine x equals negative root 3 over 2. Now, we have been working with the unit circle, and so we actually know a place on the unit circle where cosine x does equal negative root 3 over 2. So using the unit circle, we can solve for x. And let's see, it also says to
find the answers, all possible answers in degrees. So, okay, let's think about this. Sometimes I draw a unit circle out, or I just think about it in my head. If cosine is negative, it's going to be in quadrant 2 or 3. Okay, and negative root 3 over 2 means that the horizontal value is longer. So I am going to go with, there's like a 30-degree angle here. 30, 60, 90 triangle. Opposite of 30 is 1/2. Opposite of 60 is root 3 over 2. But since we're doing negative, negative root 3 over 2 because it's in the second quadrant. And so cosine is negative root 3 over 2 at this angle, okay? But also it's negative root 3 over 2 at this other angle here, and that also is a 30-degree angle. But we have to find what the angle is from 0. So, and from over here. And I know a lot of this you can kind of do in your head, but I know this is 180. So this angle right here, which is 30 away, is 150. And then the other angle that's 30 more than 180 is 210. Okay, so our answers are 150 degrees and 210 degrees. But, okay, this is where it gets a little tricky. It says all possible values in degrees. So isn't it true that I could, go around, I could go to 150, I could go to 210 like that. But couldn't I also go around the circle and come back again to 150? And then I could go around that circle and go to 210. And I could kind of do that forever, right? Go around the circle twice, 1, 2, and then go to 150. Okay, so I'm going to erase some of this because it's a little confusing. But basically, we could go around the unit circle infinite times. And so how we get all of those answers is that we add 2 pi n to the end of our answers. So the answer is 150 plus 2 pi n, okay? I could add 2 pi infinitely many times. And then 210, I could add 2 pi infinitely many times, where n is a real number, or an integer. All right, next problem. Our strategy is to extract square roots. So I'm going to first combine, or start isolating theta, which means adding 3 to both sides. And we have 4 sine squared theta equals 3. Divide by 4 both sides. Sine squared theta equals 3/4. And now this is where the extracting square roots comes in. We're going to square root both sides because there is a sine squared. So the opposite of that is square root. And then we're left with sine theta equals plus or minus root 3. And then root 4 is just like the square root of 4 is 2. So I'm just going to say sine is equal to plus or minus root 3 over 2. And lucky for us, this is another spot where, or this is another time this occurs on the unit circle, so we don't need a calculator. Where is sine equal to root 3 over 2 on the unit circle? Well, that would be, I like to draw it out, or you can think of it in your head. That would be at 60 degrees. But it would also occur in the second quadrant as well. There's also a positive root 3 over 2 there. Okay, but we were doing plus or minus root 3 over 2. So it's actually going to occur in all quadrants. Okay, so these values are 60, 120, 240, and 300. So those are our answers, and we want to add plus 2 pi n to each of them. Something I do is you can list, I'm okay with you guys listing them out like this, and then just circling them and doing, okay, all of them plus 2 pi n. But if you want to be absolutely correct, you can just add 2 pi n to each answer. Okay. Number 2, now we're solving all possible values, but in radians, okay? So, we are going to use the strategy of factoring a GCF here, okay? So that means there's something that's common between two terms, or two or more terms. So I'm actually going to get all of the terms on one side. And I'm going to write this as 2 cosine theta sine theta and minus cosine theta equals 0. Okay. And then I'm looking for a GCF, something common between both these terms. Well, cosine is in both of them. So I'm going to divide out cosine. And I'm left with 2 sine theta minus 1 equals 0. And then now I have two factors, like this times that must equal 0. So I can set both of these equal to 0. Cosine theta equals 0. And then 2 sine theta minus 1 equals 0. Okay, then the left equation, cosine of theta equals 0. Where does that occur on the unit circle? Cosine is equal to 0 at 90 and 270, or we're working in radians right now, so this would be pi over 2 and 3 pi over 2. So theta equals pi over 2, 3 pi over 2. And then for our other one, oh, I should have kept solving that. I can add 1 to both sides. We get 2 sine theta equals 1. Divided by 2 both sides. So I'm looking for where is sine theta equal to 1/2. And that occurs, again, because of my knowledge of the unit circle, occurs in the first and second quadrants at 30 degrees, or pi over 6 degrees because we're in radians, and then 5 pi over 6. I'll write it on the outside. Okay, so then these values are pi over 6, 5 pi over 6, and again, we want to add like 2 pi n plus 2 pi n, where n is an integer. All right, next problem. We're going to factor an equation as a quadratic. Okay, so there are a few ways to do this. You could just factor it straight up, or you could create an easier problem, substitute x for your trig function, and then it becomes a algebra 1 factoring problem. And then you can, at the end, substitute back sine x. So you do not have to do this. This is just how I think of it in my head. And I do think it's easier, but I'll show you this is kind of like the longer way, and I'll show you the shorter way later. Okay, I'm going to let sine of x equal x for right now. Later, I will resubstitute sine x in. Okay, if sine of x, for every sine of x, I just write x, my problem becomes 2x, instead of sine, 2x squared minus 3x plus 1. And I can set that equal to 0. Okay, this is a lot less intimidating. I can factor this. What multiplies to 2x squared? Well, it has to be 2x and x. And then what multiplies to 1 adds to negative 3. With that 2x, well, we could do negative 1. And then I would get negative 1x minus 2x, which is negative 3x. Okay, so here's our factorization. All right, now I can substitute, like I did the factoring, which I think was the hardest part. Now I can substitute sine x back in. So now instead of 2x, my factorization is 2 sine x minus 1. And instead of x minus 1, sine x minus 1. Okay, and I think it is easier to work with like this algebra 1 problem, but if you can look at this problem and go straight to this factorization, by all means, definitely do that, okay? This step in between is kind of to help you if it's too difficult to factor with the trig functions in it. Okay. So let's set these equal to 0 because these are two things that multiply to 0. So 2 sine x minus 1 equals 0. Sine x minus 1 equals 0. And solve. So I'm going to add 1. We get 2 sine x equals 1. Add 1. Sine x equals 1. Divide by 2, both sides. Sine x equals 1/2. So we're looking for where sine x equals 1/2 and where sine x equals 1. So, and this is in radians still. So if I draw my unit circle, sine is going to be 1/2 here. And sine is going to be 1 at pi over 2 and 3 pi over 2. Okay, so let's write this out. X equals 1/2, or x equals pi over 6 and 5 pi over 6. And then sine x equals 1 at pi over 2 and 3 pi over 2. Nope, it's not 3 pi over 2 because that's negative. Sorry. Just pi over 2, so that's not an answer. And then you can just say plus 2 pi n, where n is an integer. Okay, next problem. We're going to rewrite with a single trig function for this strategy. So you can tell that it kind of looks like we could combine like terms if we had the same trig function. So is there any Pythagorean identity that combines secant and tangent? Okay, so you can go back to your identities or write them out. But the third one is that tangent squared theta plus 1 equals secant squared theta. Okay, so since we have a secant squared theta here, I'm just going to rewrite it as tangent squared plus theta. Okay, so instead of 3 times secant squared, I'm going to write 3 times tangent squared theta plus 1. And then I'm going to subtract 2 tangent squared x minus 4 equals 0. All right, I'm going to multiply this all out. So we get 3 tangent, we should be working with x's. 3 tangent squared x plus 3 minus 2 tangent squared x minus 4. And then combine like terms, 3 tangent squared x minus 2 tangent squared x tangent squared x. And then 3 minus 4, negative 1. And I can add 1 to both sides and use their square root. So tangent x equals plus or minus root 1, which is just 1, right? So where is tangent equal to 1? Well, if I draw a unit circle, I know tangent is equal to 1 and negative 1 at these 45 degrees. Let's see, but we're in radians, so that's going to be pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. Okay? Pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. These instructions say in the interval 0 to 2 pi. So we are not actually going to have infinitely many answers this time around. It's just limiting us from 0 to 2 pi. So there we go for that one. Number 6, this is squaring and converting to quadratic type. Okay, when we do this, I would say this is one of the harder strategies to use, and I would use it as a last resort because we're going to square both sides, but in doing that, we'll make some extraneous solutions. So we'll talk about that at the end. But if you cannot find any other strategy to use, but you wish that you had like a sine squared and a cosine squared, one of the things I would do is square both sides. Okay? And this is not, you have to take this and multiply it by itself. So sine squared plus sine theta plus 1 equals cosine squared theta. And I can simplify this to sine squared theta plus 2 sine theta plus 1 equals cosine squared theta. And when we multiplied both sides by itself, or we squared both sides, we were multiplying in new, like, other trig functions instead of simplifying it. And because of that, we'll end up with some extra solutions that don't actually work. So let's carry on, though. I want it to all be in sine, because I have like a sine squared, a sine, and then a constant. But then this cosine squared is like, I wouldn't be able to factor it with the other sine. This is not the same trig function, so I'm going to rewrite cosine as 1 minus sine squared from our Pythagorean identity. And then I'm going to get everything on one side, and I should be able to factor. So subtract 1, add sine squared. Subtract 1, add sine squared. We get 2 sine squared theta plus 2 sine theta plus 1 minus 1 is 0. Okay, and then I can factor out a GCF. 2 sine is in both of these, and we're left with sine. And then set both of those equal to 0 for theta. So where does sine theta equal 0? Where does sine theta equal negative 1? Draw out my unit circle. Sine of 0 is going to be at 0 and pi. And sine is going to be negative 1 at 3 pi over 2. And there we go. But I did say that we were going to get some extraneous solutions here. So actually, one of these answers, when you plug it back into the original, up here, without the squares, let's see, can I erase these? There we go. Okay, if I plug in 0 pi and 3 pi over 2 into the original equation, one of them does not work. So I want you to pause the video, plug them both or all three in, and figure out which one does not work out. All right, and now okay, our next strategy is called functions of multiple angles. So this is going to, next unit or next section, we'll be looking at sum and difference angles, and we'll get to double angles. But right now we're going to kind of do a problem with it. So my goal is still to isolate x. So I'm going to add root 3 over 2 to both sides here. And now I'm stuck in this position where, okay, sine of 2 of x equals root 3 over 2. But if I had just sine of x equals root 3 over 2, that's a problem we've done before. But sine of 2x, I don't really know what that would be. So for now, I'm going to let 2x equal theta. Okay, I'm going to bring 2x back in later. But for now, I'm just going to write, instead of 2x, I'm going to write theta. And this becomes a problem I can do. Okay, sine of theta is equal to root 3 over 2. That is going to be at 60 because we're in degrees. So 60 degrees gets us root 3 over 2. And also at 120. Okay, so theta equals 60 and 120. But remember, we said let 2x equal theta. So I'm going to bring that 2x back in. And actually, since theta equals 2x, I'm going to write 2x instead. And now 2x equals 60. 2x equals 120. Now we can solve for x. So x is going to equal 30, and x is going to equal 60. Okay? And then last strategy for this section is using inverse functions. So I am first going to get everything on one side because it looks like we have a square and like a tangent squared, and then a tangent, and then a constant. So that means we might be able to factor. So let's try it. And this is one of those times where you can make it into an Algebra 1 problem if you just say, okay, for right now, let tangent theta equal x, and then we can make this equation, or make it look like this, which is a little bit more doable. How do we multiply it to 4? You could do 2 and 2, 4 and 1. I'm going to try, well, actually, no, it's going to work with 4 and 1, but you could try 2 and 2, and then if it doesn't work, try 4 and 1. And then multiply to -6, add to +5. Well, if I do a 2 right here, that'll be 8, and then I can subtract 3 to get 5. Okay, and then just bring the tangent x back in here. So instead of an x, I'm going to write 4 tangent theta minus 3. And instead of x, tangent theta plus 2. And I forgot to write that this was equal to 0, and now I can set these equal to 0 because they are factors. And then theta, well, tangent theta here is going to equal 3 over 4. Tangent theta equals -2. And then these values are not on the unit circle. So this is a problem where you would have to use your calculator and do inverse tangent of 3/4 equals theta. and inverse tangent of -2 also equals theta. And then if you put that in your calculator, let me pause and do that. You will get theta equals 36.9 degrees over here, and you would get theta equals -36.4 degrees here. Now, the reason why that second answer doesn't work is because our interval is between 0 and 360, and this is a negative number. So I'm going to draw like a unit circle. Negative 63.4 would be somewhere over here. Actually, and what is a coterminal positive angle from that? Well, it would just be 360 minus 63.4, which would be 296.6 degrees. Okay, so those are positive answers. But when we're dealing with unit circle answers, sometimes there's an answer two different places on the unit circle. So I'm also going to write this as 296.6 degrees. If tangent is -2 right here, tangent will also be -2 180 degrees away, because tangent is negative in quadrant 4, but it's also negative in quadrant 2. So I can subtract 180 to get our other answer, 116.6 degrees. So here are our answers over here. And then for the tangent, theta equals 3/4. 36.9 would be somewhere over here. And we can get tangent is positive in this quadrant 1 and also in quadrant 3. And so we can add 180 to get our other answer, 216.9. So we ended up with 4 different answers. And you'll have to check that when you do these problems. All right, that is it for section 5.3. Next, we're going to look at power reducing formulas. And this is what you can write in your important ideas. We have some power reducing formulas. Sine squared theta equals 1 minus cosine 2 theta divided by 2. Cosine squared theta equals 1 plus cosine 2 theta divided by 2. Tangent squared theta equals 1 minus cosine 2 theta divided by 1 plus cosine 2 theta. You'll notice that tangent squared is kind of sine squared formula divided by cosine squared formula. And then we could take these 3 formulas and replace theta with something else. So 2 theta, 3 theta. Okay, so for example, if we did sine squared of 2 theta, that means that in our formula, we would just double the theta. Well, cosine 2 theta times 2 theta would be 4 theta. And similarly with cosine squared, we'd get 1 plus cosine 4 theta. And tangent squared 2 theta would be 1 minus cosine 4 theta divided by 1 plus cosine 4 theta. All right, so make sure you get those written down, and then we'll do the problems down below. So the first problem says sine u equals -3/5, and it's in quadrant 4. find cosine 2u, sine 2u, and tangent 2u. Okay. So first I'm going to draw a picture. We're in quadrant 4 and -3, 5. So -3, and then the hypotenuse is 5. All right, let's do our first one. Let's solve for cosine 2u. Well, we can use a formula from before. Last section is double angle formula. And there's 3 cosine 2u formulas, but you can find there's only one. All right, I'm going to draw a picture. And it's in quadrant 4, so we have -3 is the opposite, 5 is the hypotenuse, and then let's work on finding cosine 2u. So this is actually using double angle formula from last section, and we only have sine. So is there a cosine double angle formula that only has sine in it? You can look back if you need, but it is 1 minus 2 sine squared u. And then we can just plug in what we know. Okay, well, 2 times sine squared u would be -3/5 squared. Okay, and then this is going to be 9/25. And then 2 times 9 is 18. And then I'll get the 1 in terms of 25ths. Common denominator to get 7/25. Okay, now let's solve for sine of 2u. Well, our double angle formula for sine is 2 sine u cosine u. All right, so we know sine of u is -3/5. But what is cosine? Well, going back to our picture, this would be a 3, 4, 5 triangle. So cosine in this case would be 4/5. And then multiply it all together, we get -24/25. All right, and then last, we are going to do tangent 2u. And we could use the tangent double angle formula, which is this. Or we could just say, oh, well, tangent 2u is going to be sine 2u divided by cosine 2u. So we could take -24/25 and divide that by 7/25, which would mean we're multiplying by the reciprocal, and we should get -24/7 as our answer. All right, next problem. States using power reducing formulas. Find sine of 4x. So that just means we need to reduce the power. And our power reducing formulas are all to be able to get our answer without any exponents. Okay, so sine to the 4th of x. We don't, looking back at our formulas, we don't have any sine to the 4th, but I do have sine squared, and I could just say like sine squared is sine to the 4th. And then I could take this formula, 1 minus cosine 2 theta, and plug it in there. and then it's squared. Okay, so we already reduced the power. We went from 4 to 2, but I want to get to no exponents. So what we can do here is we can distribute the 2 to the numerator and denominator. So it's going to be 1 minus cosine 2x squared in the numerator, and then 4 in the denominator. And let's multiply this out, because remember, we can't just square the 1 and square cosine 2x. It's going to be 1 minus cosine 2x times itself. And then if we multiply it out, we get 1 minus 2 cosine 2x plus cosine squared 2x, and this is all divided by 4. So we're getting pretty close. Now we only have one term that has an exponent. Okay, so what I'm going to do is I'm going to divide out the 4, so we're not really working with fractions. I'm just going to have everything over here. All right, and then, oh, well, this is actually looking familiar. Let's see if I have oh, I do. We have a formula that could help us go from, oops, squared, oh my goodness. There we go. We could use this formula and plug it in, okay? So cosine 2 theta becomes, let's see. Cosine squared 2 theta becomes 1 plus cosine 4th x over 2. All right, and technically we are done because we reduced the power, but I'm going to clean this up a little. So I'm going to now multiply out the 1/4. Okay, and then we can clean it up a little bit more. 1/4 I can write as 2/8 plus 1/8. That's going to be 3/8 minus 1/2 cosine 2x plus 1/8 cosine 4x. And then I can take out an 8, or 1/8. And I'm left with 3 minus 4 cosine 2x plus cosine 4x. And there we go. Nice work, you guys. And that is the end of chapter 5. Good luck on the test, everyone.